Hello friends, today let's solve one problem to understand how to calculate the storage capacity of the distribution reservoir. Now there is here a problem, a town having a population 1 million, average rate of water supply is 270 LPCD, and this total 270 LPCD is phased as follows. So morning 5 am to 11 am, when the maximum demand of water is there, that is 90 LPCD, and then 11 am to 3 pm it is 54, again 3 pm to 9 pm, usually again when people come back from work, again there will be increase in the water demand, so it is 81, 9 pm to 12 midnight 27, and 12 midnight to 5 am 18 LPCD. So the total LPCD of 270 is phased into 5 different times and in 5 different values depending upon the demand. Now water is supplied from a treatment plant at a uniform rate of 11.25 million liters per hour for all the 24 hours. So for all the 24 hours, rate of water supply is 11.25 million liters per hour. So for that you have to calculate the capacity of the reservoir required. Now as you know how to calculate the total daily water supply is the rate of water supply into population. This many times earlier also we have done like this. So 270 LPCD, that is 270 liters of water supplied to one person in one day. Therefore, for 10⁶ population, right? So it is instead of writing 270 into 10⁶, we will write 270 million liters, right? This is 270 million liters. Now this given demand pattern is converted into a cumulative demand, because in the mass curve method, y-axis you are plotting the cumulative demand and cumulative supply, right? So the same values 5 am to 11 am, whatever is given in the problem, those 5 time phases are given, and at that particular time how much amount of water is supplied, that is 90, 54 and all this. So this to first and second column, this is as given in the problem. Now third column is what I have written, cumulative consumption in million liters for 1 million population, right? This is the LPCD value. So you have to find out how much quantity of water is supplied between 5 am to 11 am. So this is 90 into population, LPCD, that is rate of water supply into population. So 90 into population is 10⁶. So instead of writing like that, we will write 90, here it is million liters, right? So here it is 90 LPCD. When you multiply it by population, it will be so many million liters. So 90 million liters, right? So 54 million liters, because this is 54 into 10⁶, 81 into 10⁶. 10⁶ is what? That is the population value. So therefore, as it is, we are writing, because here only we have written as million liters. Now here cumulative demand in million liters. So you go on adding. First one is 90 as it is. Second is 90 plus 54, so 144. Then 144 plus 81. So like that, total is 270. That is the cumulative demand. Go on adding, right? This is what we are going to plot on the y-axis. Now the mass curve of demand is now plotted for the data of column number 1, that is the x-axis, that is the time, and column 4 is the cumulative demand. Now cumulative flow in million liters, y-axis we are writing, and cumulative the time, right? So each block here is 2 hours, right? So 5, you start with 5 am, 5, 6, and this is 7, 8, 9, 10, and this is 11, right? 11 and then 12, 1, 2 and 3. So each unit is 2 hours. So 5 am to 5 am next morning. So 24 hours you are plotting here. And then 5 am to 5 am, and 270 is the total quantity of water supplied in million liters, 270 into 10⁶. So cumulative flow in million liters. So 270 is here, 260 is here, 270 is here. So here this is 270. So you draw a straight line here, that is the pumping or the supply line. Because you are pumping at a constant rate, you will get a straight line like this, right? And the demand line, the first value is, here you can see 90, second is 144. So first is 90, so here it is 80, here it is 90. So you will have the first dot here, 90, that is in between 5 a.m. to 11 a.m. Then 11 a.m. to 3 p.m. it is 144. So here it is 140. So slightly more than that, 144. Right. Next is 225, 252. Right, 225. 220 is here. That is in between 3 p.m. to 12. So here, sorry, 3 p.m. to 9 p.m. So 225 was here. Similarly, these 2 points. So all the values here, whatever is given on the fourth column, so 90, 144, 225, 252 and 270. So all these values we are plotting, so you will get a curve like this, bending like this slightly. Now you can see here there is no intersection between these two lines. So you will have only one ordinate, the value A will be 0 because the intersection of these demand line and supply line is not there. So you will get only one ordinate, that is between the supply line and the demand line. So only one ordinate is there. So B value is, which is the maximum ordinate you have to find in this, in between these two lines, in between this line and this line, which is the maximum ordinate. So you, according to the graph, you will find that the maximum ordinate is something around 41, value you will get 41, and this is because it is in million meters, 41 million meters. A is not there because it is not intersecting. The demand line is not crossing the supply line. So you will have only one, that is B value. So A is 0, you can see here A is 0, B is 41 million liters. Therefore, the total storage capacity is 41 million liters. So they have not mentioned anything in the problem about the fire demand and all. So we will just calculate the balance in the reservoir using the mass curve. So A is 0, B is 41 million liters. So total storage equal to A plus B. So 41 plus 0, so 41 million liters. So this is one simple type of problem which you can expect in the exam. Now there is one more problem here. For a small rural town, daily requirement of 2,25,000 liters water requirement for the town, and it is proposed to construct a distribution reservoir. The pattern of the drop is 7 a.m. to 8 a.m. 1 hour. First hour 30% of the daily supply, then 8 a.m. to 5 p.m. in the evening 35% of the daily supply, and then 5 p.m. to 6:30 p.m. 1.5 hours in the evening, again 30% of the daily supply. 6:30 p.m. to 7 a.m. in the morning, next day morning, 5% of the daily supply. So these are the given in terms of percentage of the daily supply, right? And then how the pumping is done is not like the earlier problem where 24 hours pumping is there. Here the pumping is done at a constant rate of 8 hours per day, 8 a.m. to 4 p.m. right? So this will be similar to the second example which I have told you in the master. So it is like that. I had shown two figures. One is 24 hours pumping, another is intermittent pumping. So here the pumping is not done 24 hours, it is only from 8 a.m. to 4 p.m. So how to draw this? Right? Now the total daily requirement is 2.25 lakh liters. So we'll just for easy calculation we'll write it as 225 into 10 raised to 3 liters. Now this given demand pattern is converted into cumulative demand by tabulating it like this, because for different hours you have got the different rate of demand. So the first two columns, whatever is given in the problem, these timings are written as it is, and the percentage of the amount of water used is as given in the problem. Now 225 into 10 raised to 3 liters, out of that 30%, that is used in the morning 7 a.m. to 8 a.m. So that will be 67.5 into 10 raised to 3. Then 35% of 225 into 10 raised to 6, that is 78.75. Then again 30%, it will be again same 67.5. Then 5% of 225 into 10 raised to 3 will be 11.25 into 10 raised to 3. So this is the demand in terms of liters, right? Then same thing you are going to write in cumulative demand. So first one as it is, second one you add 67.5 and 78.75 into 10 raised to 3. so it will be 146. So here just to again make the calculation simpler, cumulative demand is written in terms of 10 raised to 3 liters. So we are writing 10 raised to 3 liters here only. So we will not multiply it by 10 raised to 3 here. So we will write only 67.50. So plus 78.75, it will be 146. Again plus 67.5, it will be 213.78. Then again plus 11.25, it will be 225. That is the total quantity, 225 you should get. Whatever is there here, that you should get here. Now, the mass curve of demand is then again plotted just like in the earlier problem, using the values of column number 1 and column number 4. So here 7 a.m. to 8 a.m. like that, it is up to 9, it is up to last is what, 6:30 p.m. to 7 p.m. right, 6:30 p.m. So 7 a.m. to morning 7 a.m. So 7 a.m. to 7 a.m. here you written. You can just see here. So each block is 2 hours. So 7, 8, 9, 10, 11, 12, 1, 2, 3 like that. And the cumulative flow in 10 raised to 3 liters. So maximum value is 225. So they have taken here up to 240. Right. So the first what you are going to plot is 67. First what you are going to plot is 67.5. This one 67.5. So the first what is the timing? 7 a.m. to 8 a.m. So you can see here 7 a.m. to 8 a.m. This at 8 is here. You can see here this is 8, and at that point the value of the cumulative demand is 67.5. So 40, 50, 67. Here it is. Then next is 8 a.m. to 5 p.m. So from there to 5 p.m. the second dot will come here. 8, what is it? 8 a.m. to 5 p.m. Sorry. So 5 p.m. is here. 5 p.m. and the value is 146. So it is 120. Then here it is 147. So this is the second dot. Now third, what is the value? 213. Right? 213. That is 5 p.m. to 6:30 p.m. So 6:30 is here. Here is 6:30, and you have here how much? 213.75. 213.75. Here it is 213. And next is 225. That is 7 a.m. So 7 a.m. is here, and the 225 is here. So you will get this curve, cumulative demand curve, like this. Cumulative demand curve is like this. This you will get. Now pumping is done. What they have given in the problem, pumping is done 8 a.m. to 4 p.m. So 8 a.m. to 4 p.m. 8 a.m. is here, right? 8 a.m. is here, and 4 p.m. is here. 4 p.m. is somewhere here. 4 p.m. So you can see here 4 p.m. Here you can see. So this is the point here, and this is the point here. So you draw a cumulative supply line by drawing a dotted line from 8 a.m. to 4 p.m. So this is a straight line because pumping is done at a constant rate. So then again you take the ordinate, highest ordinate here, the highest ordinate here. So maximum ordinate B equal to 67.5 you will get according to the graph. Maximum ordinate here is A, 88.83. So add both of them. So you will get here 155.5 into 10 raised to 3 liters. Convert it into meter cube by dividing by 1000. So 155.5 meter cube is the total storage capacity. So this is how we are going to solve the problem when the pumping is not done for 24 hours. So that is how we are going to calculate. Okay. Thank you.